Good afternoon, everyone. Thank you for coming to my talk. I'm giving the final talk in today's session. In this talk, I'll show how a new piece of malware is already using ECH for its seeds traffic. Have you ever heard of the TLS extension called Encrypted Client Hello or ECH? If you are running an up-to-date Chrome or Firefox, you already have everything you need to use ECH. That Chrome keeps resume traffic private, but it also lets attackers disappear. Today, I'll introduce ECHidna, malware whose seeds traffic hides inside the ECH handshake, masquerading as a rooty CDN noise. Before we start, let me introduce myself. My name is Yuta Sawabe, a security researcher on the SOC team at NTT Security Holdings in Tokyo. Although I'm the only one on stage today, the research I represent is a joint project with my colleague Rintaro Koike. And we are focusing on malware analysis and threat research. We presented our findings last year, and we are happy to be back to share our new insights. Over the next 30 minutes, I'll guide you through our research. Let's move to the main story. In early 2024, we found a new piece of malware during a targeted attack on a Japanese research institute. The attack began with a spear phishing email. The victim opened an ISO file. Inside that ISO was a shortcut file or link. The shortcut started PowerShell, and PowerShell loaded a malicious DLL. So far, nothing special. The surprise came out at the network stage. When the DLL reached out, every packet looked as if it was going to a normal Cloudflare site. The malware was using the new Encrypted Client Hello extension of TLS, so the real seed's name was hidden inside the handshake. Because the SNI is hidden, domain blocklets cannot detect the seed's traffic. It blends in with normal Cloudflare flows. Here is the attack flow of this campaign. First, the attacker sends a spear phishing email with an ISO image attached. Windows mounts an ISO like a DVD, so no warning pop-up appears. The victim opens the ISO. Inside there is one item that looks like a normal folder, but it is really a shortcut link file. When the user double-clicks this shortcut, Windows runs a short PowerShell script, except shown in the black box. The script picks the user's temp folder. It copies a file named desktop.ini there. This file is really a DLL, but the same name looks harmless. Next, it starts run DLL and loads the DLL, calling its exported function SSL version. This DLL is just a loader. It unpacks another program directly in memory. That program is our remote access tool called ECHidna. ECHidna uses Encrypted Client Hello, ECH, so we cannot see the real server name in the traffic. Next, we will look deeper into how the loader works and how we can still detect this activity. After the loader finishes, we arrive at the real program, ECHidna. First, ECHidna is a simple remote access tool, RAT. It supports 4 commands. We will show them on the next slide. The file carries its own payload. Inside the code, we see a marker, 8 hex digits, 4 times BF. Everything after that marker is a second hidden PE file. At runtime, ECHidna uses the express algorithm to unpack this P straight into memory and runs it from there, so nothing is written to disk. Regular files can't miss it. For network traffic, ECHidna does not use the Windows TLS library. Instead, it includes a static copy of boring SSL. This lets the attacker build a custom handshake and turn on ECH without dropping extra DLLs. The attacker can send 4 main commands to this route. The command setting makes the imprint send its current configuration to the SIDS server and also keeps a local copy on the host. The other 3, download, upload, and share, are the usual route functions for file transfer and remote code execution. Please note, we analyzed only the malware sample itself. We have not yet seen an attacker use these commands live, so their exact purpose may still change. This table shows the JSON keys we see in every SIDS messages. The whole packet sits inside ECH. After decryption, we see these fields. CID and ID both hold the host ID. They tell the server which machine or victims is talking. Results keeps the reply from the route, shell output, and error code, or the current config. With just these keys, the attacker can tag each host, move any file, and run live shell commands, all inside one encrypted TLS stream. The malware needs a label for every victim, so each SIDS request carries a host ID. The ID is always 8 hex characters. How is this ID made? The code joins 3 local variables: the MAC address of the network card, the flow of the running process, in our sample, run_dll32.exe, a fixed campaign string inside the binary, often a date-like value. Then a small custom routine squeezes this long string down to 8 hex characters. The host ID stays the same after a reboot or even a second infection. ECHidna keeps every parameters it needs for SIDS communication in malware config: the SIDS domain, port, HTTP path, and the polling interval. On the first run, ECHidna uses the hard-coded defaults inside the DLL. When the operator sends a setting command, the malware writes these same values to an encrypted file in all user profile folder. This file keeps its name and survives reboots. On later runs, the loader looks for that file. If it is missing, it falls back to the defaults. We do not know how attackers update this config. The setting command only saves the current values, and no other command updates them. We assume that, instead, the attacker dropped a fresh encrypted config file using the download command. ECHidna uses 4 small tricks to slow us down. First, a custom base64 alphabet. The data still looks like base64, but the character set is different, so normal decoders fail. Second, it builds each JSON-like message by hand. No JSON library codes appear. This makes the decompiled code bigger and hides the unusual JSON function names. Third, all traffic uses raw WinSock. By skipping WinHTTP and WinNet, the malware avoids proxy outconfig and some ideal hooks. Last, the binary links boring SSL statically. All crypto runs inside the malware, so Windows Script API calls never show up. Each trick is very simple, but together they delay both automated tools and human analysts. We must watch the network, the endpoint, and even process memory to catch ECHidna. We have finished the host-side part. Now let us look at ECHidna's seeds traffic. First, I will explain how ECH connects to the server. Then, we will look at how ECHidna hides its true seeds server inside that handshake. Encrypted Client Hello, or ECH, is the next step after encrypted SNI, first shown in 2018. ESNI hid only the hostname SNI field, and that was not enough, so the design changed. In the new standard, ECH encrypts almost the entire client hello message, not just the SNI. That hides the hostname from anyone who is on the path. Adoption moved fast. Since September 2023, Chromium 117 and every browser built on it ships with ECH turned on by default. Firefox 119 did the same. On the server side, Cloudflare enables ECH for all plans, and other CDNs such as Fastly are in beta. After years in an experimental phase, ECH was approved as a proposed standard in July 2025, and it is expected to receive its RFC number and become a full standard within the next few months. For normal users, this is great. The hostnames still stay private. For defenders, however, the easy hostname signals disappears, and ECHidna abuses that blind spot. Let's follow the diagram and watch the ECH handshake step by step. In this example, we assume the targeted domain is served through Cloudflare with ECH enabled. The client first needs an ECH config. It asks DNS for an HTTPS record and gets two things, a public name and a public key. Using that data, the client builds two ClientHello messages. The inner one holds the real SNI. The outer one shows only the public name. The client encrypts the inner message with the key, puts it inside the outer message, and sends the whole message to the server. The server reads the public name, uses its private key to decrypt the inner blob, and then runs the normal TLS steps, server hello, certificate, finished. After both sides send finished messages, the tunnel is fully encrypted. No passive observer on the path ever sees the true host name. Now, let's zoom in on each step in more detail. Before any ECH handshake, the client must fetch an ECH config. It could use normal DNS, but many privacy tools and ECHidna itself prefer DNS over HTTPS or DOH. DOH hides the lookup from classic DNS sensors and looks like normal web traffic. The client asks for the HTTPS record over a helper domain. In the JSON response, there is a field that starts with ECH equal. The long base64 text you see on the slide is the encrypted configuration blob defined in the ECH draft. The client decodes this blob and keeps it until the TTL runs out. When the TTL expires, it fetches a fresh config. With the config cached, the client is ready to build its encrypted client hello. Here is the decoded and parsed ECH config. It contains many fields, but we only need to watch 3 of them. First, public key. It encrypts the inner client hello. Only Cloudflare holds the matching private key. Second, public name. The cover SNI you see on the wire. Every packet uses the same domain name, Cloudflare ECH.com. Third, version, config ID, and cipher suites. These values tell the client which draft, which algorithm, and which key set are valid. With these 3 items, the client can now build its ACH and start the hidden TLS session. After the client gets the ACH config, it builds the client hello and sends it to the server. In Wireshark, we can still read a few lines of the handshake. The packet says outer client hello, so we know this is only the wrapper. We also see the chosen cipher suites, the config ID, and the size of the payload. But the payload itself, the inner client hello with the real host name, stays fully encrypted. So a sensor can confirm that ECH is in use, yet the true seats server name never appears on the wire. After receiving the outer client hello, Cloudflare Edge reads the config ID, picks the matching private key, and tries to decrypt the payload. If decryption fails, the handshake simply falls back to a normal TLS connection without ECH. If it works, it learns the inner SNI and finishes a normal TLS handshake. Server hello, encrypted extensions, certificate, then finished. Now, the tunnel between the client and Cloudflare is fully encrypted, but the request still has to reach the real seats server. Because Cloudflare works as a reverse proxy, it either answers from cache or starts a second TLS session to the attacker-controlled origin. To anyone in the middle, every state still looks like plain HTTPS traffic to the Cloudflare domain, cloudflareech.com. The real seats host name never shows up, so the attacker gains an end-to-end encrypted path for command traffic. And that completes the ECH handshake. It's getting a bit complex, so let's compare the seats connection with and without ECH. Without ECH, the client sends a normal TLS handshake. The SNI shows the attacker's real domain, so anyone on the path can read the name and block it. With ECH, the client encrypts the real client hello and wraps it in an outer one. The outer SNI is always the cover name like cloudflareech.com. So the real inner host name stays hidden. That is why ECH is a strong cloak for attackers. Defenders must look for other signals because the host name is no longer on the wire. Now that we understand the ECH handshake in theory, let us see how ECHidna gets the information it needs to start that tunnel. Before it can open the ECH tunnel, the malware first needs an ECH config. It sends a DOH query for the HTTPS record of crypt.cloudflare.com, and this looks strange at first. You might expect the malware to ask for the HTTPS record of its own seats domain. But Cloudflare reuses one ECH config for many customer zones, so this single lookup works for any seats domain. and the real malware domain never appears in DNS. The sample holds 6 public DOT resolvers, and it tries them one by one. If a resolver fails, it waits, doubles the delay, and moves to the next. As soon as one resolver answers, the malware decodes the ECH-based 64 blob, caches it for the TTL, and builds the encrypted client Hello. This is the point in the code where ECHidna builds and sends its encrypted client Hello. First, the routine runs 2 short checks. Is an ECH config already in memory? And does the SIDS domain still resolve? If either check fails, the handshake is skipped. When both tests pass, the malware builds one outbound request. It fills the outer client hello with the public name from the cached config and hides the encrypted inner client hello inside. It also puts the 8-character host ID into the URL, so the attacker can recognize the victim even if the public IP changes. Finally, the code resolves the SIDS host name, sends the packet through its own copy of boring SSL, and finishes the TLS handshake at Cloudflare's edge. In one step, the malware hides its real host name, tags the victim, and opens the encrypted tunnel without exposing a readable SNI on the wire. We have finished the part about how ECHidna works and how it hides inside ECH. Now, let's move to the detection part. What signals still remain, and how defenders can spot this malware in real networks? To catch ECHidna, we watch 3 data layers and then combine them. First, DNS traffic. We flag any HTTPS record whose ECH echo field comes from Cloudflare. Second, the TLS handshake. We look for the outer SNI Cloudflare ECH.com together with the encrypted client Hello extension. Third, the endpoint. We watch for a short process chain, Explorer, PowerShell, run DLL, which rules a random DLL from temp directory. When these 3 signs appear in a short time window, it is very likely to be infected with ECHidna. The next slide will look at each layer in detail. Here's a normal DNS response. We can still read the part that says ECH echo and the cover name Cloudflare ECH.com. That gives us a simple rule: flag any HTTPS record whose ECH echo field points to Cloudflare. The TTL is only 300 seconds, so the malware must repeat this lookup every few minutes until holding SIDS connection. Extra signals we can count. If the malware uses DOH or DOT, the DNS message is encrypted. If your system can decrypt TLS, open the TOH traffic and look for the same ECH echo text. If you cannot decrypt it, switch to the next cruise we will show. When a site enables ECH on Cloudflare, the config sets the public name to Cloudflare ECH.com. In Wireshark, you see that cover name in the outer client hello exactly what the slide shows. The real host name sits inside the encrypted client hello extension, so it never appears on the wire. The problem: Normal web browsing to any ECH-enabled site uses the same DNS and TLS pattern. So network data alone is not enough. This rule helps mainly in environments that block ECH, like enterprise servers. In those environments, any ECH traffic is unusual and worth a close look. On the host, we hunt for one clear pattern, PowerShell spawning run DLL to load a DLL. Two details make it stand out. First, there is no parent browser process. Explorer calls PowerShell directly. Second, the DLL sits in temp folder, is unsigned, and is not a normal Microsoft file. Most endpoint tools can flag that with a short rule. When we link this host alert with the ARIA signals, we have three independent clues that point to the same event. Together, they give a strong, raw false positive way to detect ECHidna or any similar malware. Let me finish with short points. First, ECH hides the whole handshake. With the common name Cloudflare ECH.com, host name filters see nothing. Second, ECHidna mixes that clock with DNS over HTTPS DOH and an in-memory DLL loader. So one click is enough for a very quiet infection. Third, each layer still lacks a clue. If we link an ECH equal DNS response, a TLS handshake whose outer SNI is Cloudflare ECH.com, and the host chain exploder PowerShell run DLL, we get a strong low false positive alert. That's our take on ECH-based C2. Thank you very much for listening to my talk. If you have any questions or comments, feel free to send me an email later. Thank you.
Thank you very much.